Welcome for the today's lab session. Today we will be seeing about measurement of power and power factor. Okay, power is the amount of energy which is required to do the work. Okay, if you need to do a work, you need some power. Okay, so in electrical or electronics, power is represented as voltage into current. Okay, then what is power factor? Okay, power factor is present only in alternating currents. Okay, it is not present in DC currents. Okay, uh, here if you see this figure, here the alternating current source which is delivering power to the resistive load. In this figure, the alternating current source is being delivering power to the inductive load. Okay, in this figure, the same alternating current source is delivering power to the capacitive load. Okay, then what is power factor? Okay, here all the power source are delivering power to the load. Okay, here the power is delivered to the resistive load, here it is delivered to the inductive load, and here it is delivered to the capacitive load. For the three circuits, you can see three voltages. Okay, here this voltage source is different, this voltage source is different, and this voltage source is different. Here the different in sense they are different in voltage ratings. Okay, it may be 10 volt, it may be 12 volt, it may be 5 volt. Okay, all these voltages are AC voltages. Okay, at the same time, you see the currents which are flowing through them. Here is the current which is flowing through the resistive load, and this current is different from the inductance and capacitive currents. So similarly, all these currents are different. So here the inductive current is I, and here you can see the capacitive current is IC, which is flowing through the inductor. So where is the power factor coming here is, you see the graph. Okay, if you connect an alternating current source or alternating voltage source to a resistive load and you are supplying the power to the resistive load, then a current will be flowing and a voltage will be present in the power source. When you plot the voltage and current in a graph, what you will be observing is, here this one is the voltage waveform and this one is the current waveform. Okay, if you plot these things, then you observe that the current and voltage waveform starts uniformly at zero position and ends uniformly at zero position, and similarly it again ends uniformly at the zero position. The voltage magnitude and the current magnitude may differ. Okay, you see here the voltage magnitude is higher than the current magnitude, but in the x-axis, in the time period, both are starting at the same time and ending at the same time. Similarly here also in the negative peak also, they are ending at the same time. So when alternating current power source is connected to a resistive load, then the voltage wave and the current wave are in phase with each other. Okay, here the in phase term represents that both starts at zero position and ends at zero position. Okay, so the in this resistive load, the voltage wave and current wave are in phase. So what I am going to tell you is, here the difference between them is zero because both are starting at the same point. So you cannot differentiate or difference the each point. So you see the pi will be equivalent to zero and it is known as unity power factor, because if pi is zero, then cos pi will be equal to 1. Okay, if pi is 0, if you substitute pi is equal to 0 in cos pi, then cos pi will give you a value of 1, which represents unity power factor. Okay, if you move to this one, you see here, this is the AC source, and similarly this one is the inductive load. The AC source voltage is different and the current which is flowing through the inductor is also different in terms of magnitude. Okay, the voltage magnitude is different, the current magnitude is also different. While we plot the same, in a graph, what you observe is you see here, this one is the voltage wave and this one is the current wave. Okay, uh, you see in the previous case both starts at same zero position, but in inductive circuit you see the voltage starts at zero position, whereas the current waveform is lagging. Okay, it is not starting at zero position, it is lagging some distance. Okay, so this difference from the time period of starting from the zero position is represented as pi. So here you see the pi is 0 and it is said to be as unity power factor, but here in lagging power factor you see here the difference of pi in magnitude is present. So this pi magnitude, that is the pi difference in time period, will give you a lagging power factor. So if cos is lagging, that is cos pi has a value, say some value. Okay, we will see this in practical sessions. Okay, if the cos is lagging, then it is said to be lagging power factor. Okay, similarly, if the voltage source, alternating current source, is delivering power to the capacitive load, then what happens here is the current starts leading the voltage. You see here, now the current wave, you see the voltage wave is starting here, but the current wave have already started before this point. Okay, so the current wave starts at this position, it is not shown in the graph. So it is said to be leading power factor. Okay, so if a resistive load is connected to a AC source, it is said to be unity power factor because there is no time difference between the zero crossing of both AC voltage and the current present in the waveform. Whereas inductive load is connected, you see a lag in difference. Whereas a capacitive load is connected, you see a leading difference. So in connecting the components such as resistor, inductor and capacitor to AC voltages, you will have leading, lagging power factors as well as unity power factor. Okay, I think all have understand the power factor concept. Let us move to the practical session. Okay, this is the circuit diagram. Okay, here what we are doing here is uh, you see, this is the main terminals. Okay, this is the main terminals R, Y, B. Okay, this is a three-phase connection available in our laboratory. Okay, then this three-phase connection, you have a supply voltage of 440 volts. Okay, it is highly dangerous. If you carelessly put your hand in this thing, you will be thrown out. Okay, so this is highly dangerous voltage, 440 volt at 50 hertz supply. The three-phase voltage will be present at this terminal. After this terminal, you see here a fuse is present. Okay, this one is the fuse. Three fuses for the three-phase lines. After here, before here, you see a triple pole single throw switch is present. TPS TS. Triple pole single throw switch is present. Okay, you can turn on and turn off the total supply with the help of this switch. In a single throw, it will turn on all the 3 points. In a single throw, it can turn off all the 3 points simultaneously. So the simultaneous operation of all the three switches is represented by the connected dashed lines present in the switches. Okay. After the fuse, you can see the circuit is entering into a auto transformer. Okay, what is mean by auto transformer? You may say distribution transformers which is present in your streets. Okay, all our homes are powered by the distribution transformers present in our streets. You may not see an auto transformer. Okay, auto transformer is present in our lab, and the main purpose of the auto transformer is you can vary the supply voltage from 0 to maximum voltage which is present here. If you give a 440 volt AC supply as input to the auto transformer at the output terminals, this is the output terminals of the auto transformer and this is the input terminals of the auto transformer. Okay, if you input the supply into the auto transformer of 440 volt, you can get an output of 0 to 440 volt adjustable voltage in the output terminals of the auto transformer. Okay, after this point, you see here, this is the neutral point connected. Okay, after the output of the auto transformer, what we are going to do is we are going to measure the voltage. Okay, so what we are connected here is the voltmeter. To measure a voltage, you need a voltmeter. This voltmeter type is moving iron. Why moving iron is used? Because to measure a alternating current, that is a AC current or a AC voltage, you need to use a moving iron type of instrument. Otherwise, you cannot measure the voltage. There are two types of instruments basically. One is permanent magnet moving coil instruments. Other one is moving iron instrument. Okay. A permanent magnet moving coil instrument is shortly noted as PMMC. Okay, this type of instrument is used to measure direct current, whereas moving iron instrument is shortly noted as MI. Okay, moving iron instrument is used to measure alternating currents. Here you can see a three-phase alternating supply is inputted into the auto transformer. So the output of the auto transformer is also an alternating supply. To measure alternating supply, you need to use a moving iron instrument. So moving iron instrument is represented by a sine wave in it. Okay, you can see this one is also a moving iron ammeter. So to measure the voltage, you are connecting the voltmeter across the terminal R and Y. Okay, since it is a three-phase connection, you know that VRY, VYB and YBR carries the same voltage as other phases. So we no need to connect the voltmeters in all the three phases such as VYB and VBR. You can connect only one voltmeter at the terminals of VRY, and so you can measure the voltage across all the three phases will be the same. Next, what we are going to do is we are going to measure the current which is flowing through the resistive load or inductive load. Here is the load. Okay, three-phase variable load. We are going to use a resistive as well as inductive load to measure the capacitances. Okay, uh, now we are going to measure the current flowing through this. To measure, you are going to connect a ammeter. You all know that voltmeters should be connected in parallel, whereas ammeters should be connected in series. Okay. Next, what we are going to do is to measure the power which is delivered by the circuit, you are using a wattmeter. We are having two wattmeters, W1, this one, and W2, this two. Okay, these two wattmeters are used to measure the power which is delivered to the variable load. Okay, to do this, we need two wattmeters, and this method is known as two wattmeter method. Instead of using single wattmeter, we need two wattmeters because if we use a single wattmeter, you cannot measure the power accurately and it will give a false reading. To measure the power correctly, you always use a 2 wattmeter method in alternating circuits to measure the three-phase power. Okay, on explaining this, inside the wattmeter, what we will be having is a current coil. This is the current coil of a wattmeter, and this one is the pressure coil of the wattmeter. Okay, a current coil of the wattmeter should be connected in series. You see, this is the ammeter which will measure the current. So, inside the wattmeter, there is a current coil. So, as in ammeter should be connected in series. In the same way, the current coil is also should be connected in series. You see, the current is directly connected to the current coil and it is directly delivered to the R phase of the load. Whereas in this pressure coil is present, their two terminals are here. In the pressure coil, what you need to do is pressure coil represents a voltmeter. So inside the wattmeter, there will be ammeter coil as well as a voltmeter coil. Okay, to give power to the pressure coil or to measure the voltage which is present in here, you need to connect the pressure coil in parallel. To do this, you need to connect one terminal of the pressure coil here and the other terminal of the pressure coil to this point. Okay, you can see some markings such as M, L, C and V. Okay, I will explain you what are these markings. Here C represents common point, where common point of the wattmeter and M point of the wattmeter are short circuited. Okay, M and C will be short circuited and connected to the ammeter terminal. Whereas here the L terminal represents the load. So this end of the wattmeter should be connected to the load directly, and the another end V terminal should be connected to the opposite phase. That is, if the wattmeter is connected to the R phase, then the other phase, that is the V phase, should be connected to the Y terminal. Similarly, on coming down over here, you see the same wattmeter setup. There is a current coil as well as a pressure coil. You see the current which is flowing from the B phase is directly connected to the current coil and it is delivered to the B phase of the load. Similarly, you know there is a pressure coil and this pressure coil should be connected in parallel. So the common point of the pressure coil is connected with the M of the current coil, whereas the other end V end is connected to the opposite phase. Why it is opposite phase is it is the M point, common point is connected in B phase, so this V point should be connected in Y phase. Okay, so this is the complete setup of the measurement instruments. After the measurement instruments, you say the currents or the voltages which is delivered to the load is R line, Y line and B line. So these three lines are connected directly to the load. Here the resistive load and inductive loads are used. We will see this later. Okay. Okay, this is the calculation procedures. Okay, I will tell you how to do the experiments. First, I will show how to calculate the readings. Okay, you need to measure the voltage, current, wattmeter 1, wattmeter 2. So there are four values you can measure from the experiment. Okay, so voltmeter, ammeter, wattmeter 1 and wattmeter 2. So there are four values. So if you do experiment for a single row of the tabular column, you need to measure the voltmeter value, ammeter value, wattmeter 1 value, wattmeter 2 value and write it down here. Okay, this is the voltmeter value, this is the current, that is the ammeter value, and this is the wattmeter 1 value, and this one is the wattmeter 2 value. Okay, next what we are going to do is, this one is the multiplication factor of wattmeter 1 and this one is the multiplication factor of wattmeter 2. So the multiplication factors referred as the scale multiplication factor. In a wattmeter, the scale is from 0 to 600. Okay, but the power which is going input will be higher. To do the scale to have a higher ranges, what they will do is just multiply the scale by 4 or multiply the scale by 2 or multiply the scale by 3. So this multiplication factor will be shown at the back side of the wattmeter. It will be physically present as a label in the back side of the wattmeter. So as per the connection, you can find the multiplication factor and enter it in the tabular column. For our wattmeter, it is 4. Okay. Next, what we are going to do is, this one is for resistive load. For resistive load, we are going to find the power factor and the power delivered to the load. Okay. To do this, what we are doing here is, first we need a formula. Okay. To find the formula, here it's a formula: pi is equal to tan inverse of root 3 W2 minus W1 divided by W1 plus W2, which will give you the pi value. Okay. Here you see the line voltage is 440 volt, current is 3.6, wattmeter 1 is 360 and wattmeter 2 is 380. So to find the pi value, what you need to do is put tan inverse of root 3 into W2. Here the W2 represents 380 into 4. What is 380 into 4? It is 1520. Okay, first write this 1520 and 360 into 4 is 1440. Okay, so here you see W2 minus W1. This means you need to subtract these things. 1520 minus 1440 divided by W1 plus W2, nothing but 1520 plus 1440. Okay, what the value will be coming here is tan inverse of root 3 into here 80 will be coming divided by 2960. Okay, so you should use a scientific calculator to find the value, which will be equivalent to 2.63. Okay, so the pi value is nothing but 2.63. So you need a cos pi value. So cos of 2.63 will give you a value of 0.99. Okay, to find a tan inverse, you can use a scientific calculator. Here, the cos value is 0.99. Okay. After here, to find the total power, what you need to do is W1 plus W2. Here we have already added these things, which is nothing but 2960. Okay. So this is the calculation step for finding the power factor of a resistive load. So the important point over here is you know that in a resistive load, the sine wave, okay, this is the voltage wave. Okay, and this one is the current wave. Okay, in theory, what we have studied is the two waves, that is the voltage wave and the current wave. In a resistive load, they will have 0 at the starting. They will start similar and end at the similar 0 point, and this will also end at the similar 0 point at the same time. So the pi value will be what? 0. So cos of 0, what will have? Cos of 0, what you have? Cos of 0 will be 1. Okay, so similarly here you see in this thing the values of power factor should range from, here these values should come from 1 to 0.99, okay, or 98 is the maximum value you should put in here. Okay, this is for checking. Okay, if you have a lot of values over here, if you calculate these using the formula for resistive load, you know that the pi value is 0 in theoretical. Okay, if you do in practical, you will have some pi value which will be similar to 0.99, 0.9995, 0.9895, some values will be present, but it should range from 1 to 0.98 only. If it is more than that, if you get a value like this 0.76, then this value is wrong. Okay. Okay, let us move to the next calculation, which is nothing but for inductive loads. Okay. Okay. For inductive loads, you can see the line voltage is 440 volt, line current is 1 ampere, wattmeter 1 is showing minus 56 watt, and the wattmeter 2 is showing 96 watts. And here for inductive loads, here the multiplication factor is 2. Okay, you will be using a different wattmeter for measuring inductive load. Okay, to do this, what you need to do is you need to multiply minus 56 into 2. What you will have is minus 112. Okay, similarly 96 into 2 you will be having 192. Okay, so the formula is same. Here you will be having root 3 W1 minus W2 divided by W1 plus W2, which will be having a tan inverse. Okay, so to do this, what you need to do is pi is equal to tan inverse of root 3 into W1 minus W2, which is minus 112 minus 192. Okay, divided by W1 plus W2. Okay, which is nothing but minus 112 plus 192. Okay, while solving this, you will get a pi value of 0.95. Okay, the pi value is, sorry, 0.15. Okay, to find the cos pi value, you need to substitute the value here. Okay, cos of 0.15. What will happen here is you will get a power factor of okay, wait, I have made a small error. Here the pi value is not 0.15. Here the pi value is minus 6.58. Okay, so here also the cos pi value will be minus 6.58. Okay, the power factor, that is the pi value, cos pi value. Okay, cos pi power factor is nothing but 0.15. Okay, I have wrongly written. Okay, so what you need to do is you need to substitute this value here. Okay, 0.15. Okay, similarly, you know W1 plus W2. You need to add these two things and write it over here, which will be nothing but 80. Okay, so this is the calculation for inductive loads. For inductive loads, what you have to get a value of, the value should be from 0.19 to 0.001. Okay, these values should be present. This range should be present in this tabular column. Okay, other than these values, other than these ranges, if you say you get a 0.9 in this tabular column, then it is wrong. Okay, for inductive load, you know, this is the voltage waveform. Okay, whereas if you see the current waveform, it will be starting like this. Okay, so what you'll be having here is lagging power factor cos pi. Okay, when you make a difference between this value and this value in time period, this is the time axis. If you have these time period values in difference, you have a pi value, and this lagging power factor is represented here. Okay. I ask you to note these values into your tabular column. And here is the another values for inductive loads also. Please note these values also in tabular column. Okay, this is our lab setup. Okay, here you can see these are the meters which are connected to the load. Okay, here you can see this one is the voltmeter, this one is the ammeter, and these two are the watt meters. Okay. Here, this one is the auto transformer, and this one is the main board which we are going to connect the input supply. Okay, here you will get the three-phase input from here, and from the three-phase input, you should use the connecting wires R, Y, B. So these three wires are used to connect in the input terminal of the transformer. This is the auto transformer. This is the output terminal of the auto transformer, and you can adjust the top end. Here is the adjustable knob. If you adjust this end, the output supply will vary from 0 to 440 volt. Okay. Okay, here you see this one is the voltmeter. Okay, and here is a ammeter, a wattmeter, and this one is the another wattmeter. Here this one is the resistive load. Okay, for resistive load, here you need to connect the three wires. This is the R wire, Y wire, and B wire, and here are three switches. Okay, three switches represents six switches. Six switches represent six different resistors which are present inside the resistive load. If you turn on this switch, a resistance of power 0.5 watts will be added. If you turn on this switch, another 0.5 watts of resistance will be added. Okay, here you can see the switches. Okay, 0.5 kilowatt switches. Each switch, if you turn on this switch, 0.5 kilowatt will be added. If you turn on this switch, another 0.0 kilowatt resistor will be added. There are six such switches. Okay. Here is the circuit explanation. You can hear in this video also. Okay. Okay, here is the connection. Okay, practically it will be connected. Okay, you can see this wire is connected over here. Sir will be explaining you all these things in the practical way. Here is the main board. Okay, here is the main switch, which is triple pole single throw switch. Okay, this switch is triple pole single throw switch, and these are the three main terminals R, Y, and B. Here it is. Okay, this is R, Y, and B. Okay, this is the input terminal of the transformer. Here is the R, Y, and B. From the switch, you will be having fuses. After that, you need to connect to the input terminal of the auto transformer. From here, from the main board, three wires will be connected to the auto transformer R, Y, and B. See, from here, it is connected to the three terminals of the auto transformer. After that, from the output side, what we are doing here is from the output side, you will be connecting to the voltmeter, ammeter, and wattmeter. Okay, this is the variable knob which is present at the upper end. Okay, here it is. Okay, from here. Okay, from this point, it is connected to the voltmeter, and from this point, it is connected to the another terminal of the voltmeter. Okay, this one is the voltmeter. There are 2 points. From the auto transformer, we will be connecting to the 2 points of the voltmeter. Okay. Next, it will be connected to the ammeter. Here's the ammeter. So you can see here. Okay, you can see here. This is the ammeter. So it is connected from the voltmeter. It is the connections are going to the ammeter. Okay, you can see here clearly. This is the common point. This is the 20 amps point, and this is the 10 amps point. So this is a 0 to 10 amps, 20 amps ammeter. You can have a range of 0 to 20 amps. Okay. In this experiment, we will be using up to 10 amperes. So what we are connecting here is the common point is connected here, and the another end of the ammeter, this 10 amps is connected. Okay, if you need a 20 amps, then this wire should be disconnected and connected to this position. So you should multiply the scale by 2. Okay, so you will get a reading for 20 amps ammeter. Okay. Here it is very clear. This is the common point. This is the 20 amps connection point, and this is the 10 ampere connection point. Here, see the scale. It is for 20 amperes. Okay, if you connected the position in 20 amperes, you should multiply by 2. If the pointer is saying 6, then if you connected in the 20 ampere terminal, then it is 12 amperes. Okay. Okay, this is the 20 ampere connection. From here, after the ammeter, you are going to connect it to the wattmeter. Okay, here is the wattmeter. I'll show you clear. Here it is. Okay. Here you can see this is the common terminal, and this one is the M terminal. Both are short circuited, and this M terminal is coming from the ammeter. Okay, and here this is the L terminal. Okay, this L terminal is going to the load. You should connect this thing to the load. And this one is the V terminal, where this V terminal should be connected to the Y phase of the auto transformer. Okay, so you should remember that a wattmeter has a ammeter and a voltmeter inside. Okay, so the ammeter is known as current coil, and the voltmeter inside is known as pressure coil. So the ammeter coil, that is the current coil, should be connected in series, and the pressure coil should be connected in parallel. Okay, this is the another wattmeter which is being connected. Okay, I will show you. Okay, after this connection, you can see here the 600, and this one is 300, and this one is 150. Okay, we are using a supply voltage of 440 volt. You know that thing. To measure the 440 volt supply voltage, you cannot use 300 because it is lesser. So what you need to do is you should connect it in the 600 volt supply. So you should use this 600 terminal. And here you see a switch, forward reverse switch is present. Why this switch is present here is, if the wattmeter pointer is present here, okay, from 0 to full scale, okay, if the wattmeter pointer goes to the negative terminal, okay, I'll show you. Okay, here it is. Okay, if the wattmeter pointer goes below 0, what you should do is you need to make the switch in reverse. Okay, if you put this switch in reverse, this pointer will be in positive direction. So if you take a reading, if the switch is in reverse, if you put the switch in reverse and you take a reading of 600, then you should write it in the tabular column as minus 600, because you have reversed the switch. Okay, this is the resistive load, okay, which are connected to the wattmeters. Yeah, here is the practical session starting. You need to supply voltage by increasing the knob. Okay, You can see the pointer is moving. See, the pointer is moving as the voltage gets increases. Okay, see here, the pointer is reaching voltage of 440 volt or 415 volt. Here you can see the in clear. See, a voltage of 415 volt is applied to the voltmeter. Okay, see, it is very clear. Okay, it is 415 volt. After this thing, a ammeter is connected. Now the ammeter is showing 0 because the load is not turned on. Just the voltage is applied, but the load is switched off. If you turn on the load only, then the ammeter will show the current which is passing through the load. Okay, otherwise it will show 0 only. And here the wattmeter will also show 0 because the load is not turned on. Okay. After the turning on of the load, the wattmeter will and ammeter will show you the readings. Okay. Now we are going to turn on the load. Okay. You are turning on the load. Okay. You see, this is the main switch for the resistive load. First, you need to turn on the main switch over here. After turning on this, resistance of 0.5 kilowatt being turned on. If you turned on this thing, you can see the ammeter deflection of 1 amperes from 0 to 2 amperes. Now it is showing 1 ampere of deflection. Okay. And wattmeter is showing a deflection of 100 watts. Okay. Both the wattmeters will show you deflection. So after taking the readings, just write down in the tabular column. I have given you the readings in the PPT. So directly you write down the readings from the PPT into your tabular column. So similarly, you need to turn on each and every switch. Okay, first you turn on this switch, take a reading. After that, you turn on this switch. You should not turn off the switch. Okay, you should keep the switch in on position. Then you should keep this switch in on position. So this will add you 1 kilowatt. After that, if you turn on this switch, it will add you 1.5 kilowatt. After that, if you turn on this, it will add you 2 kilowatt. Similarly, you should turn on each and every switch consequently and take 6 readings. And note the readings in the tabular column. Okay. Okay, I need to show you the difference. Okay. Here. Okay. This is the wattmeter of multiplication factor 4. Okay. One student had asked the doubt why it is 4 and why it is 2. Okay. This is the unity power factor wattmeter. This wattmeter should be used to measure the resistive load. Okay. I will show you the inductive meter also. Clear. Okay. This one is the inductive meter having a power factor of 0.2. You see in this wattmeter they have represented as 0.2. This represent the meter is used for measure inductive loads. So different meters are connected. So multiplication factor is different. For resistive load, the multiplication factor is 4. And for measuring inductive loads, this wattmeter having a multiplication factor of 2. Okay, I will show you the inductive load. Okay, this is the inductive load. Okay, in previous case you have seen the resistive load, and this one is the inductive load. Here, in the inductive load, three wires are coming out from the inductance, and it is being connected to the wattmeter. Here are the three wires. Okay, these three wires are connected to the wattmeter. What you need to do is you need to change the inductance as you did in the resistive loads. Okay, and you need to measure the values of here. You can see it in clear. You need to rotate this thing and change the inductance value, and you can measure 6 consecutive readings, and you should fill the tabular column and do the calculation and find the power factor of inductive load as well as resistive load. Thank you.